I'm Aaron. This is Tom.
I'm Tom. And we're going to show you today Tableau that's not Superstore.
Yeah.
Yeah, this, yeah.
Other one. Flip it around. Yep.
There we go.
Okay.
Maybe.
Is it?
Okay.
All right.
So the first, what we're doing here is classical orbital dynamics in Tableau. And the first thing we did was collect a data set that Tableau could use. And that needed a lot of work.
It was very messy.
Prep, Telnet, download from NASA, from JPL. But we're going to get that data. Then we're going to do a history lesson with some vizzes showing what Plato would see and what Copernicus finally declared was the real solar system. And then we have simulations at that point using the reality, the truth that the data set from NASA produces. And then at the end, we'll just get to play around with the data set. It's super cool.
Yeah.
Along the way, if there's anything that you want to see or know or how we did whatever, if it's prep, what's going on? If it's prep or if it's any of the calcs that we do in the vizzes, please ask.
Yeah, the whole talk is going to be in Tableau. We're not using PowerPoint or anything else. So we're actually functional here. Anything that we can pull it open if you want to see exactly how the calculation works, we can do that.
Yep.
So
you know what's going on?
we seem to have a loose
We've
wire.
got a strobe going.
We'll keep talking while we're figuring this out.
So here's what we know right now. This is an artist rendition. This is not an actual photo, but we know we're one small thing in this big, huge, enormous set of things. But the question is, how is it that we got here? Oh, I'm sorry. We've reordered.
Yes.
So this is introducing how we got the truth data set. So JPL on Jet Propulsion Lab produces a data set that is accessible to all of us. And they have a Telnet interface. And Aaron hooked up to this Telnet interface to download the data. It sounds easy, but it's big, nasty text files. And
NASA limits the amount of data you can download in a chunk to about 3,000 rows. So you have to download multiple times if you want to get a full data set. And it's quite a lot of data.
I was just using, there you go.
There. Okay, so here's the website if you want to go there and download it yourself. We got 785,000 different asteroids. We've got 3,500 comets and about 100, there's several hundred items in the major body catalog alone. And today we're just going to work in the major body catalog. We're not going to do the comets and the asteroids because we want this to be a little bit faster. We only have an hour for the talk. If you guys had half a day, we could do a whole set and sit and watch the spinner, but we wanted to keep this fast. So let's see, the Telnet, I wrote a little bit of custom code to get the data out of the Telnet. There's a couple different ways to do it. They have a web interface. They have a email batch file interface. Part of it is I was learning to code, so I wanted to push myself and do the coding. So I don't know how to best put that. Several hackathons, so my code is very messy because I would do it for a few days and then for 6 months I wouldn't touch it and then I'd do it for a few days and I'd learn stuff along the way. So it gets better as it goes along. And then I used the extract API to put it into a hyperfile because it's a lot of data, and bringing it in and doing an extract, it's a little painful. here is the website, and this is live in Tableau. So if you're ever doing a presentation or working on something, you can get into, you just embed a website. We have Mars here, so, oh,
Oh, no.
that is the problem with doing it live, though, is if you don't have a good connection, which is all right, though, because we put in a backup. This is the text file that you would be seeing in just a second if that website had worked. And it's a messy file, and you can see, let's see.
At the bottom, here are the data that tell you where, in this case, the Earth is,
Yes.
I believe.
Yes, this is the Earth. So it's X, Y, and Z, and the velocity X, Y, and Z. And we cut this off, I don't know how many rows we have here, 10? But there's 3,000 rows, 3,000 rows of this vector. And then if we go back up to the very top, you can tell that over time, NASA has collected this data from different scientists, because sometimes the units are on the left, sometimes they're on the right, sometimes the scalar is on the right, and sometimes it's in over here. This one is fairly clean. But all of that, we don't really process that well. This kind of file, it's great for reading, but it's not great for bringing into a database. So.
It's big and nasty.
So go ahead and switch over. So I think it's this way. Nope, it's the other way. There is that file again. Oh, I didn't make a full screen. I'm sorry. Hold on just a second. This desktop. Oh, no, I closed it. So I have a Maestro file. You have it.
I have it on here, yeah.
Okay, so we can have all kinds of backup today. Today is an episode, an exercise in backing up and making sure you're prepared.
So 5 should be playing now.
Yep. I put 5. All right. Well, even prepared, we're not doing very well. Anyway, so I put this all into prep, and there was a lot of massaging of the data, and I have several flows. And about how many people have used prep? How are you guys liking it so far? Pretty good?
You made it up.
Yeah.
Oh, come on.
Okay, could you maybe stand up just right here? All right, so with prep, I was doing a lot of moving things around, and then towards the end, this is the final flow that I did. And as you can see, things are all joined very nicely. So
we showed you a strobe of the...
It feels like it. At the top is one of the models, and I was pulling out the number of bodies, and I rejoined it so I could have the number of bodies. The other models are sprinkled throughout, so the models that we were creating. At the bottom, I have NASA's gold standard, and I'm kind of just pushing them together so we have kind of a central data set when we're in Tableau. And that way, we just have to do one set of calculations. We don't have to repeat for different data sets. Okay.
Bummer.
Well, why don't we go ahead and switch back to
Is this 4?
3. Yeah, the next one over. There we go. And if you're super interested in the flow, I'll pull that up again later.
Yeah, don't worry.
That one right there.
Yeah.
Oh, that's right, because it's on that page. That's why I didn't see it before.
Okay, so how did we get to where we are now? In Plato's time, people would look up into the sky every night, and they would see all the stars just lying there still, except for about 5 of them that would move around a little bit. And Plato's design was about simplicity, about spherical, circular. And everything, of course, had to orbit the Earth because the Earth was the center. So that was Plato's model. And forward is here.
It's coming.
Yeah. So this was Plato's model. Earth's next was Moon, and then Mercury, and Sun was out there. The Moon and the Sun were easily visible and predictable. The others moved around, and Plato decided, okay, since it's a simple model, I'm going to describe it this way. This is actually a historical, I think it was 1538 or something, so not Plato's time, but these are his numbers. And this is about, Earth-centered, and just the precision of these, let's see. Yeah, the precision, this is 27 days, 8 hours for the moon orbit, 70 days, 7 hours for Mercury. It's a little short, 273 for Venus, then of course 365. But I mean, look at these numbers. 277,084 and 1/3 leagues from the center of the Earth is where Jupiter lies. That's that's awfully precise. But we used these numbers and we put them into Tableau and created this phys. So this, unfortunately, for Plato and for science at the time, would not explain things like the movement of the 5 stars that moved. Sometimes would cross the sky, stop, turn around, stop, turn back, and keep going. This wouldn't explain that. That's called retrograde motion. And the second thing another thing it wouldn't explain is the stars would dim like the moon does. If it's in phase or out of phase, the planets that he thought were stars would get dim and get bright, and that couldn't be explained by this. And that model predicts nighttime movement of the stars in this straight line. So you would not ever see anything random that they were obviously seeing. But the math gets a whole lot harder. So this is a model Ptolemy put together of, again, the Earth at the center, and this is showing Venus and Mars and the Sun. But the orbits here are sort of a little tiny orbit inside. The little tiny orbit is called an epicycle, and it's orbiting inside a bit larger orbit called a deferent. And this actually does and can describe some retrograde motion, which is why Ptolemy put this together. And this was 1300s, 1400s. And we lost it. OK. Yeah, the math is a whole lot harder, though, with this model. But we still pulled it into Tableau with those numbers. This here is Mars doing its loop-de-loop. Up closer, we could zoom on this if.
Sure.
And
you want to see Venus? So one of the nice things about doing stuff in Tableau is you can just do stuff, and it'll still work.
Yeah, so, I mean, you get some nice spirographs drawn this way, but, this actually does describe some retrograde motion with these loops. Oh, and this was just a fun bit of Tableauism here. We decided to see what Ptolemy's model would look like if the sun were at the center, and
so this is exactly the same model we were just seeing. We just shifted it over.
Just from a different viewpoint, right?
Yeah.
And the last screen looks sort of like this screen on half of it, so it sort of does still describe the reality they saw. Nighttime, this is predictive from Ptolemy's model. And let's see, you can see, are we not going fast enough?
Oh, let's see.
Yeah.
Just took a second.
So you'll see Mars is the red one here, and it will eventually stop and turn around and do its little retrograde dance. Oh. Yeah, so
and each one of these data points is at midnight. So as we're going along, we're simply just seeing a day. We're treating the Earth as a point in the solar system, though, so we're not adjusting for where you're standing on the hemisphere, or, if you're in the northern hemisphere or the southern hemisphere. But this is generally what you will see at night if you go out and look at the sky. And it's hard to tell.
You have to do it a whole bunch of days in a row, though, to notice these loops. This is, unfortunately, this is way faster than they do their little loop-de-loops. So yes, it was sacrilege to assert that the Earth wasn't at the center. And until Copernicus, and I don't think things went terribly well after Copernicus proposed this, but he proposed it again in 1543. So the math gets a whole lot easier, and I could draw that, but it's the same old, effectively, sines and cosines of round orbits around the sun. So what we did now is we started to model the orbital mechanics from high school. Remember high school? With this is classical algebraic gravity. So at any instant, this is Newton's formula for gravity, and in Tableau we can predict the position of the Earth given. Well, I'll show you. The model is we started January 1st of 2000 and decided, and from the data set, we found out this is where the Earth is, this is how fast the Earth is moving, X, Y, and Z, and from that we walk forward exactly 10 years, but at whatever resolution we want. So this was just a matter of showing how to model something and then how to test it. So we have three models we're going to go with. First, we're going with a complete flat, planar Earth and Sun on the same plane, nothing in the Z direction. And so this is reality, and we're going to keep coming back to this. But since it's a roundish orbit, it's sines and cosines that these model to. This is reality, though, remember, but this defines a round orbit. The Z is kind of strange, and we'll talk about that in a bit, but our model doesn't describe that. So here we are. This is our model on top of the reality. And what you can see, and we can see a little less well unless I zoom in. So Z, you can tell I'm saying it's completely flat, but if we zoom in here, you can see some.
Size it up so it shows up better. So it's hard to judge how this is going to show up on a giant screen. On our screen down here on the Mac, this is actually super big, and it's like, oh, we need to make it smaller so we can see it better. But then when we get to the big screen, it's too small.
And it just went black and white on me. What just happened?
Yeah, you got it. All right. And why don't you talk to the model, and I'll get us to this.
So if you notice in the middle here, our model line is the thin line, and the pink line is reality. It's not quite hitting exactly where, it's not down the center of the line. So the model's a little bit off, of course, because we're only looking at X and Y.
So this is what we were talking about. If you guys were asking how to see this, so I'm going to pretend that I heard in the background, how do you make that bigger? And I'm going to do that right here while he's talking.
Well, I'm going forward, actually.
Okay, go forward.
But you're on the slide.
I'll go forward. I'll go forward.
Right. So this is what I was saying. All of these describe a round orbit. So this was just showing the X and Y, and they make round orbits. We can't really tell how bad they are unless we're looking at the sines and cosines, because it all looks pretty perfect. We're not going to be able to tell the difference.
Okay. So while you're talking about this,
so
here's the error.
Here's the.
Okay. Oh, sorry.
So this is showing how bad our projection is. And as you see, it's a linear increasing badness. I mean, we start out perfectly on day 0, and on day 1, we're a little bit off, and then we keep on. With each year, we get maybe a little bit slower, worse, but but continually linear bad, of course. And the reason for this, and this is kind of cool, this is looking at we're looking down the X and Y axis right here. And this was just a cool viz. And you can see the Earth kind of wiggles that's actually the frequency of the moon, of course. But you notice the orbit of the Earth is on a small Z slant. I mean, this is a very exaggerated Z, but the orbit is not on the same plane as the sun, as the orbit of the Earth is tilted to NASA's z direction. I mean, there's no z direction of the sun, but at some point somebody said, okay, that's up. So I just think that was just, I liked watching that. So now we're gonna throw in the z, but we're still going with just the sun and the Earth. And again, here's truth. Here's what we are aiming for, and this is our model now. Again, you can see we're not quite square in the middle of the x and y, but we do get a little bit of the wiggle now on our model z. It's interesting that it is collapsing downwards, and we'll with the full truth of the data set, we can predict that properly with like what the reason for all of that is Jupiter pulling downwards, or everything else actually. These are 20,000 kilometers. And notice, yeah, the difference. This is negative 100 million kilometers. And yeah, so the x and the y are way bigger scale than the z, but yeah, Earth does wiggle a little bit in the z direction. Yes, you're saying reality here. You're saying gets worse. Is that what you're?
You're actually had a more accurate prediction over time previously. Before you were only off a couple, like 2,000 kilometers. But here you're off 10,000 kilometers.
So this one, we are also holding, I can't tell if it's a step on the cable and it does it, or if I step the right direction. And so this model, it's not a completely accurate model because the acceleration that we're using is fixed over time. We're using the actual acceleration the Earth was feeling. And so the Earth starts to move, but we're still using the acceleration it would have felt where it was. And part of that was because we want to be able to bring you along. We don't know what kind of audience we were going to get. So if you didn't understand orbital mechanics, we wanted to be able to say, hey, this is, a piece of that. And so.
But that's a really good point.
It's excellent.
Yeah, I don't know why that is. We had a viz that we actually don't show today, but we did have a viz that did the in-bodies of all the planets, and we did predict this. Well, actually, it pulled this back up to the proper z. Yeah. But
and some of it,
we'll show a bit of that.
We'll get into that later. There's a piece we'll touch on later that may answer a bit of that question.
Yeah.
This may sound like a very interesting question, but are you modeling it in elliptical orbit?
Yes.
Okay.
Yeah.
Yes. We're modeling. All I'm looking at. We can show you the. All I'm looking at is the acceleration from the position and the distance, using Newton's law. So that's going to predict, given day 0, it's going to predict where it's going to end up.
Yeah. And since we're using the initial velocity from NASA, it's going to shoot off in an elliptical fashion and then be sucked back in. And this one doesn't show it the greatest, and in fact, the other ones we've been showing, they get a little bit squished. We haven't scaled our vises exactly, because this isn't just science. This is more of a, how can we do things in Tableau, and isn't this fun, and it's not Superstore.
So the model is pouring it back into
Yes. Yeah. Yes. Yeah. The pink and the yellow, the thicker pieces, and the gray here are NASA.
So this would be much more severe.
Yeah. So
Mercury's a problem because it goes so fast,
Yeah.
and we're absolutely going to talk about that.
Yeah. See? All right, I'm going to stand over. I'm going to
Okay,
stand
so-
over here.
So how good is this one? It's actually nearly identically bad to the first one. I mean, that's 2 lines. That's the first model to the second model. So, all right, so let's add the moon to the Z. Here's truth again. And there we go. It's still, we do get the now periodic of the orbit of the moon, pulling the Earth up and down, but we're still decaying in the Z direction for whatever reason, and we're still 20,000 kilometers off at the end. But this model is far better. This model is far better. So those are the other 2 stripes. This is the new. The blue is the new, including the moon model. So we're only 1,000 or 1,000,000 meters off after 10 years, which sounds like a ton, but here's the real. This is the scale of it. So these are those 2 lines we just saw, and that's the distance from the Earth to the sun. So, okay, and we're modeling here not every instant. We're not doing calculus here. We're modeling here. I think this was every 4 days or so. So we're taking a snapshot. And we're like, all right, we'll throw the Earth to where it goes in 4 days, and now we'll throw the Earth again. And so we can tweak those things. We don't have the workbooks visible here, but this viz will be available to you, and you can tweak those parameters and see, or tweak those parameters and see how good or bad your predictions get. Okay, so, but now this is where we would have put the in-body model in, but we decided that this was just a cool data set, and it's, sure, we can show you that, okay, we can predict where the Earth is. The Earth's right here, but we just wanted to play with the data set.
So this next section, it's if you guys want to see something, ask. So this right here is the 8 bodies. We've generated this using a little C++. This model is a little bit more refined, but it's also set up to, say you want to, this one has, we're at the sun is at the center right now. Now the Earth is at the center. And so we can switch this around. This one only has just 8 bodies, and it's a predictive one. So I also put in there some error calculations. So in here, it's looking at each of the objects and saying, how far off is it? And so some of the objects are a little bit further off than other objects. Mercury is one of the worst ones, and that's because it's traveling so fast. And I sampled at about a minute, and I threw away everything. So I just took the first minute of every day, and then just kept going on. I'm sorry. So if you put the sun back at the center, then Mercury.
Yeah, this is Mercury at the center.
Yeah, so Mercury. So if you hover now, the error. So the Mercury is saying now that the sun is really far off. And that's because of the way that the calculation's set up. So if you switch it and the sun's at the center and the sun says Mercury's really far off. And really the solar system is very relative. I mean, it doesn't really matter who's at the center. It just makes the math a little bit harder.
But this was produced, these positions were produced by
These are mine one.
right, by doing gravity math on every position, every planet and its position at the current instant through the model of truth.
Yeah. And so the next one, this one is the NASA's version. I'm sorry, I forgot I put the slide in here. This is what we're seeing from whatever body we're at. So this is that previous one, and you're looking up at the sky, and these are where everything is at. So, and this one also changes. So this is, if you're at the sun, you're looking out in the solar system. And now we're on Earth, looking at the solar system, which is just gorgeous. So this is part of the thing where we were talking about. This is just a lot of fun to look at. And then if we pull open Jupiter, Jupiter's looking back at the sun, and everybody's racing around the sun, right? So if you lived on Jupiter, you would be seeing something completely different than when you're living on Earth. And then, so now we have the NASA version. And this guy is thinking just a second because we unplugged him and plugged him back in again. And you can see on here that there is a lot of hairs. Oh, and now we've moved. We are still around Jupiter. The parameter that I was using to select where we're at down here is the same parameter through all the pages. So if I change one page, the other ones change. So Jupiter right now is
I
looking.
just put the sun at the center.
You want to put the sun in the center? So I think, what do we got here? This is Saturn. And all right, so now the sun's at the center. So now where we were at was this hairball here. And part of the problem is that Jupiter and Saturn, they both have a massive number of moons. And that's why there's so many lines there. And that's one of the things that makes the math so hard. If I'm doing that two-body calculation, then I have to do it for every body that's in the solar system with every other body that's in the solar system. So it's a self-join. So if I have 1,000 bodies, then it's 1,000 by 1,000, and then that's just one row. And then you just keep doing that for however many time steps that you want. You want to go ahead and zoom in to the Earth area? So if we come into Earth, you'll notice that there's a lot here. And most of this here is satellites, spaceships that we've put up, things that have come and gone. So this one right here, you want to hover over that guy? That is one that's orbiting, one of our satellites that's orbiting the sun. And it goes out and comes back, goes out and comes back. And it's taken lots of pictures. Let's see, Mercury is right here.
Yep.
And then Mercury is one of our problem children because it's traveling so fast. But NASA, they've got a lot of really big computers, so they didn't have the same problems we had. Yeah. I have removed them because I have so many lines already that when I add those in, it becomes hard to see, especially on the small screen. On the bigger screen, it's actually not so bad. This is much nicer.
Yeah, the question was to show the Lagrangian points.
Yeah, sorry. And a Lagrangian point is basically if we took multiple bodies, who here knows what a Lagrangian point is? Good, good. And who doesn't know? Excellent. So earlier when we were calculating the sun, Earth, and the moon, Lagrangian point would be this point where the gravity is kind of zero-ish. You know, it kind of equals out there. And there's multiple points. There's points before and there's points after. And it's just kind of the way the math works. And so if you were to sit at one of those points, you wouldn't feel as much gravity as if you moved off of it. And if we had the larger asteroid data set, the 760,000 pieces, there's a large body of asteroids that we drag in those Lagrangian points because they don't have gravity to push them out. And so we kind of drag them around the solar system with us as we go. And I would love to show that. And if I can get Tableau to buy me a supercomputer, we'll have that talk.
This is from the moon.
Yeah.
This
The moon
what
is excellent.
things look like. Yeah.
And you can see that Jupiter is doing the loop-to-loop now, and Saturn's doing the loop-to-loop. And the Lagrangian points, where would they be? It's hard to tell on all. So, like I was saying, we have so much here. Do you want to zoom in on Jupiter there? We'll take a look at the moons or Saturn. So as these guys are traveling, their orbital mechanics have evened out over time, right? So everything we're seeing has been running long enough that it doesn't degrade it doesn't degrade while we're looking at it. There's a few of them that'll crash. But all of these moons are whipping around Jupiter and they're still not hitting it. So they've kind of become into a nice balance. And then you want to go ahead and zoom all the way out. And so one of the reasons we started zoomed in on this viz is we have these guys that are out here and corkscrewing out. Anyone want to guess what these ones are? These.
Again, this is from the viewpoint of the moon.
This is from the moon. So what was it? Voyager? Excellent. Anybody else? Comets? I think we have one comet in here. I think this one's the sliding spring comet. And then, yes, we got Pioneer, Voyager 1, Voyager 2, and I think New Horizon. And the reason that they're going in loop-to-loops
Pioneer
instead of a straight line is because we're looking at it from the moon. If we look at it from the sun, then they go in a straight line. And it'll take just a second for it to update. And so one of the reasons we like giving this talk or talking about this subject is if we ever have science teachers come in. When you're giving a lecture, this is an excellent way for students to see what you're talking about. And as you can see, it's very dynamic. And we have the tooltip and all that stuff. So that's just a plug, because I went through school and it was on the chalkboard and very slow and very dry.
And the math is hard, and Tableau is doing so
Yes.
much of it for us. And in
Absolutely.
fact,
No, this is it's still in kilometers, but it looks like AUs. Part of that is the screen is, these now have faded in between, but on my screen over there, all the grid lines are exactly the same. So there's some color changing going on the projector. And that's something we know about, and we've been looking into it, but we haven't figured out a good feature for that. Okay. Any questions? Anything you guys would like to see? Yeah. Absolutely, yeah. Oh, this is the view from whatever object. So this is the sun. This one is a satellite that's it's studying the sun. That's why it's got the big loop. And then I had a question over here. You want to see the
Yeah.
which calculations? You guys want to see the science calculations, or you want to see the Tableau drawing calculations?
I think they want to see the center of the universe question.
Science.
Oh, okay.
Okay. Center of the universe question.
No,
So
not the answer.
what we do, most of this, like we said before, we just pulled down the data from, let's see, thank you. We pull down the data from NASA and we get X, Y, and Z. And we're going to compute because we changed our size. Once we have X, Y, and Z, and right now, NASA is my model. So I have NASA in a couple of places. But to draw this, we have the earlier geometric shapes, but for NASA, we just use X, right? And use X, Y, and Z. So this screen right here is using X, Y, and Z. The next screen where we're looking out, the view out into from wherever you're at, we're using spherical coordinates. So we just do a simple transformation. And some of the radiuses some of the locations go down to 0. So I make sure that my radius doesn't ever hit 0, so I don't get to divide by 0. But it's simply the arc cosine of Z over R. And R is X squared, Y squared, Z squared, and then square root. And then for the other piece, we do phi. And for that, it's an arctangent. And there's 2 arctangents in Tableau, and this one I like because it's a little bit easier to type in. But the other one is almost the same. You just put a slash instead. Yeah. I love doing it. I absolutely do. But because it's only a 60-minute talk and there's so many data points, it loads and loads and loads, and then it'll step. So when you came in, the piece I had in the beginning was a page shelf, and it was stepping and moving the 8 bodies through, and that works great because it's only 8 bodies. Last year when I did this talk, or I did a talk similar to this, I had just the planets, and I had them running around, and it was a lot of fun. It's just gorgeous. It's mesmerizing. So, yeah. I haven't yet because it's not my day job. But if it was my day job, I would love to include flattening of the Earth, putting the radius of the Earth. The values that we have here would allow us to calculate when things collide. And if I can get all the asteroids down, calculate when they collide. And then NASA also puts out the time difference, so some delay on light, so we can guess and say, well, NASA's model's maybe not so good, you know, because they're missing this piece or something collided or something is lensing a little bit of light. But yeah, that would be awesome. Yeah, any more? We love questions, so if you guys have more
will
questions.
You show the center of the universe?
Huh? The center of the universe. It is in Fremont. Just right next to our office, there's a signpost, and it says it's the center, so they must be true. Let's see, what are more interesting?
This is how we did the center of the solar system.
Oh, yes. So the calculation here is a table calc, and I average it because if I have multiple points, then it kind of shows in the right spot and I don't get a scaling error. But the lookup, if you put the lookup calculation in and you don't include relative position, then you have to claim it here in the default table calc. You want to go ahead and click on that? And for this
and
one,
it says in the tooltip here too, right here.
yeah,
Lookup values.
yeah, we're getting very good at helping people out because table calcs, they're not the easiest thing. You know, you kind of have to understand what they're doing. There's a bit of a database windowing operation that's going on. For this one, you select the name, and then it's relative to the parameter, which is the center of the solar system. And I made that parameter down here. Tom was just pointing at it, and I simply loaded all the names from the name column. You can do it however you want. You could just put the top names in, the names you want people to have access to. This calculation will fail on the 8-body one if you pick one of the satellites, because the satellite's not actually there, so it'll just draw a blank screen. But once you have everything in, if you wanted to see what the solar system looked like from Voyager, we could pick that and it would draw.
I was hoping we would be able to look up what the solar system looks like from the Tesla that's going to Mars right now. But it's not in the, well, it wasn't launched in 2010.
No, it wasn't. I have an updated data set, though, that does have the rocket man. So NASA has been tracking him. Is the dummy a him?
It, yeah.
The dummy that's driving the Tesla
Starman,
through
right?
the solar system. Huh?
It was Starman, right?
Yeah,
Wasn't it?
Starman, yeah.
So I suppose him.
So, actually, you want to pull up Voyager for the center of the solar system? You might have to scroll a bit to get to it. And actually, go big screen.
So go what?
Full screen and then Voyager. So, any more questions on how the sausage is made, or yeah?
While you're doing that, in your model, does the sun move?
It does.
All the other planets?
It does. Yeah. Yeah.
How does it reflect it?
It's a point on. If we took out the adjusted one where we're picking the center, he moves around. When we pick the sun as the center, he stops moving and everything gets adjusted to anything that he was moved. So, and in fact, in NASA's model, when you download a big enough set, the sun makes a flower. So in NASA's model itself, it is also moving. Yeah. Yes? Yes. Yeah, so one of the things I would love to get to, so the question is, have we thought about calculating gravitational pull of objects that we don't have on here? And I think it would be wonderful if we got to the point where our error was so small. So when we looked at like Mercury, and it was going way far out. If we could get that down to almost nothing, and then say, well, wait, there's still this bit of error there. And in order for that error to be there, we have to have a mass. Somewhere in this area, or in these areas. And then we could try to calculate where, I think they're calling it planet X is, There's several new dwarf planets that are way out in the Kepler belt, and they're in the asteroid data set. And so, yeah, so if we can get the asteroid data set, I think that's going to be where we find that answer. And I would love to do it. And I am going to ask them for a supercomputer, and they're going to tell me no. But I'm going to ask. What's that? I can't
Did
hear.
you ask NASA yet?
Oh, no, I haven't asked NASA yet. I don't know. It would be interesting. They were at my talk last year. Is NASA here again to this year? No? Oh, man. All right.
So this is Voyager's view.
Yeah. And so Voyager is interesting because we slingshotted Voyager around planets. We were lucky enough to be in the time when the planets aligned, and you can see right here where we have these sharp turns, and that's because we used the gravitational pull of Jupiter to get a boost in our speed to get Voyager further out into the solar system.
Is the sun maybe straight
I believe it is there for part of it and then takes a turn due to the slingshotting. And in fact, Voyager 1 and Voyager 2 are very interesting. I don't have it in this one.
The sun is this stripe up the middle, yeah.
Up the middle, yeah.
Which makes sense.
Yeah.
I guess it kind of makes sense. Doesn't make sense.
Yeah.
It's like we're going away from.
Everything's getting tighter as it goes up. Yeah. If you look at this with the z direction added in, which I don't have drawn in this workbook just to make it go faster, Voyager 1 and Voyager 2 hit a certain point, and then one goes up and one goes down. And it's a really cool thing to do the page shelf on. Explorer? Satellite? I'm sure it is in there. Let's see.
That's Voyager 2.
Not all of them are in good naming order. So in that text file, I grabbed the names out of the third line of the text file, and they were entered very uniquely. So the one scientist put date,
see an Explorer.
name, / object you were orbiting / horizon JPL. And another one had, this is a special object. And then a date, and then what the date meant, and then the name. So,
I could not find an Explorer in here.
yeah. We can check afterwards if you want to take time. Sure.
Given how long some of these calculations might take, at what point, let's say you were in your room with some data scientists, and figure out whether you bring it into Tableau and model it, or have you versus connect to like MATLAB or Python, whatever. Like, at which point?
So the question is, allow me to rephrase, how can we best, I was using the word all day yesterday, and now I've forgotten it. Optimize, thank you. Not that you said it, but I just looked at you and I knew.
You're welcome.
So how do we optimize these calculations? So if you know that the data, so the result of the calculations isn't going to change, you're going to want to do that outside of Tableau and then bring it in as a calculation. But if it's going to change, so if you have a parameter that you're wiggling, you can do that inside of Tableau. But in addition, Tableau has a calculation. So if you pull up the calc table or the calc formula, there is a piece where we can send a calculation off to R and off to Python. Am I allowed to say more than that? Have we released more than that? Our company's gotten so big, I lose track on what stuff has been released.
Is that in here?
So then if you type in there script, over that, yeah, script, real, string, int. These guys here, if you use those, you'll put inside a bit of Python or a bit of R. It'll send it off to a server, an R server, a Python server, and do the calculations and then bring it back into Tableau. So then you don't have to do something and then bring it in and then go back and then bring it in.
In some of our models, we did have the problem of circular references because the position affects the acceleration, and the acceleration affects the position tomorrow, right? So that's why the simple models we were doing with the sine curves were not, the sun wasn't moving.
We got 10 minutes. Okay. All right. So you want to put up the survey slide, and then we'll open it up for general questions, since I don't know if you guys are running off to other
I think this is the last one. Is this the last one?
Oh, you want to do more?
Thank you for coming.
Yes, thank you for coming. Yeah, we're going to have more, absolutely more questions. We just want to, for the guys that are going to go, we're going to put up the survey slide. So what do you got?
Is there something similar to what you guys did here for in the realm of particle physics or astrophysics?
You can do this with whatever you want to do this with. So that was actually one of the points we forgot to touch on in the beginning. Whatever your data set is, you can do it in Tableau. Some of the stuff you have to be a little creative. I've seen a wire mesh cow in 3D and with parameters, so you could rotate it around.
My father-in-law measures his tomato plants and how fast they grow,
Yeah.
based on what he's watering. Yeah.
You want to put the survey
Yeah.
question up?
I just want to show this.
Oh, yeah. So this is awesome. I love this.
This is, yes, how things look from that thing. So,
Yeah, so don't forget to do your surveys.
Survey.
All right, and then we had another question. Okay, yes. First and the second.
I was going to ask, the satellite we have total around the sun,
Yeah.
do you see its perspective?
Yeah, yeah. One of the things I would love to do, and I wasn't able to get in for this one because the data was so messy, is to get the radius of objects. And part of the problem is that one scientist would put the radius here, and then the units, and then, like I was saying before, because then we could scale the objects, and so the sun would be big, and Jupiter would be big, and the satellites would be tiny, and it would be even more impressive to see.
what's the object called that we want the polar satellite? Do you know?
There is a, I believe it starts with an H. Yeah. I don't recognize those ones. How about if you do sun-centered and then hover over what's ever nearest the sun?
Got it.
All right, and then you had a question.
Yeah, are you going to share this workbook, but I don't know if you can go on to share
The prep flow, I need to clean it up a little bit because it's kind of messy, and if I give it to you and you're going to be like, this is garbage. But there's a lot of me, there's a lot of me exploring in there, and I just kind of left it in because I was the only consumer. But yes, I want to try to get that up. We need to find out when I can publish up, so it's going to take me maybe a couple of days to clean it. Yeah, a sunset, high node.
I know. Okay. This is Ulysses. This was the big swoopy.
So this one, yeah, goes way out and then comes around the sun and then goes way out again.
That
That
is
is
awesome.
impressive.
Thanks for finding this one. Yes.
Yeah,
And high node, you said?
high node. Yeah,
So,
thank you.
first of all, it's kind of concerning to me that NASA keeps data like that.
So
Yes.
what I suspect is that they have a different interface than what they give us. And what they're giving us is a,
No, they have people that clean my,
yeah, okay.
so they do have people that will read stuff, but they read it, but that's how it goes. And usually what happens is, so each satellite that gets launched will have, its own schema and structure. So it actually take so much more work to clean something than my structure. Adding different instruments that everything that you wouldn't really use.
Yeah,
So in some weird way, it's actually better, because, based on that.
sure. Well, then the other issue is some of this data is actually fairly old.
Very, very old.
Yeah.
Like, you can't tell Voyager perspective from the based on or things like that, so it's a lot easier to keep stacking it that way.
Yeah. So I think we're kind of leaving the other side of the audience. So we're discussing the NASA's formatting of the papers and
Like, what they could have done is run like a little bit more poly.
yeah,
Poly and that kind of stuff.
yeah.
Mostly interested in how
So I wrote code, and then now that prep has come out, I started this project. I've been with Tableau for 7.5 years, and I work in QA. And so one of the jobs of QA is to break the product and make sure that you guys don't break the product. And for hackathons, I would go out and say, hey, that's something I'd like to see. And so I'd start bringing it down. And so this data set I've been working on for several years, before we hit 8.0, I believe. And as we've come along, I've been able to get bigger and bigger chunks of it. And originally, I was trying to parse the data in it with my own custom code, and it was a pain. I hated it, because I would run it, I'd have to change the order, and then I'd have to run it again, and then change the order, and to make sure that the data wasn't, I was using regex replace and regex grepping. But now we have prep, and so now I'm exploring it in prep, and I'll look at a section, and then I'll write a section of the flow, and to pull out that piece. And then I'll export that into a normal database table. And then I'll look at another section. I'll try to figure out what the best way is to format that so that I can pull it out into a table. Yeah.
More of a general question.
Sure.
Your two backgrounds.
Well, go ahead, Tom. I'll let you start.
I'm super interested in using Tableau, and I've always been mathy, but not astronomy as much. I'm on the runtime team on Tableau. We work on the back end of the visual pipeline. So we're rewriting everything that's drawing a mark to the screen, or anything to the screen. We're refactoring that. So this was just fun for me, and yeah, seeing Aaron's data set was like, yes, let's do this.
So me, I was just kind of being a bum, and then I went to school late. And when I was going to school, I wanted to get into CSE, but I didn't have the grades for it. And so I fell back at the thing I was good at, which was physics, and I was going to school part-time, so then I was like, oh, well, I'll just take extra classes and extra classes. And, hey, you know what, if I do these classes and those classes and get this many, and then, so I ended up with a BS in astronomy, a BS in physics, a BA in math, and a minor in history. So it's kind of just, it's a thing that I'm good at, and then I came to Tableau. I lucked out. I got on the Tableau, and it's just been fun. Yeah.
The way you're describing the sections within prep, are you noticing that there is consistency within portions? Is that what you're saying?
Yes. So when I'm in prep and I'm looking at this data set, I can tell that there is a scientist that entered 20% of the asteroids, and there's another scientist that. Yeah, so there's chunks that are consistent, but then when it's outputted, they don't tell me who did what. Then I have to go through and I have to do a regex and say, hey, this section kind of looks right. Put it in this pile, and then parse it. And then this section looks like this one over here, so put it in this pile and parse it. I haven't looked at it yet. I've been so busy on my team, I haven't. 8 years ago, yeah, I'm aware of it. Yeah. Yeah. Back then, I knew everything that was in the product, and now it's awesome that we have so many devs and everything, but I don't know everything well enough, and I need to learn it, though. So I'm going to try the data modeling. I'm going to see if that will work. Yes?
Did you search for any community groups that are advocates to try and clean up the
No.
data?
Not yet. So most of this I've been doing as QA work or hackathons. I think it's still kind of messy, and I think once I get it cleaned up, I would like to hand it back to NASA and say, here, this is something you could use. Here's a flow. All you do is just open up your database and push it all through, and you'll. Oh, I'm sure there's tons of people. I assume, though, that people have their sections. I'm assuming that somebody's like, I love Titan. I love everything about it. Here, let me clean this piece so that it looks like what I want it to look like.
Well, I would guess that if somebody did do a parser and were happy with the results, they would parse that into some format and perhaps make it available for them.
Oh, yeah, absolutely.
To get more up-to-date information much easier than
Absolutely, and that's something we're advocating in Tableau. We're trying to figure out how to make it to be a good data advocate out in the public space. So I can't say too much more because insider trading rules, and I don't want everybody to get into trouble. But this is something that Tableau itself, the data, not astronomy data, but any data in general, we're very passionate about that. We want to make sure that people are using good data governance, making good decisions, and removing that. So when you're out there trying to see and understand your data, you don't want to be cleaning your data. You want to be seeing your data. Yeah, we want you to make it as just easy as possible and skip by that. So prep, extract API. What's the other one that for cleaning data that we have? It's escaping me right now. I think we have another one that helps in the managing of your data. Conductor. We just released it, which is prep on the server, right? So, any more questions?
Remind me of what your step size was in the calculation.
So for the modeling, Tom?
This one was 1 day.
Yes, so this is 1 day.
I even mean for your calculations. You really, it's just for the acceleration calculations. You really go one.
Tom's was 4 days.
I
Mine
can open
was
those
a
up.
minute, but I threw away the rest of the day. So I did all the minutes in a day.
By the minute, but then only kept one.
I only kept one because we wanted to be able to,
So
make it
that
snappy.
was that.
Thank you for coming, guys.
That's modeling almost calculus. If we're going every minute, but only taking a snapshot of position every day. So it's not calculus because we're still, like Mercury's still doing crazy things in that minute, but it's closer, and we don't, like previously when we were looking at Mercury in the 1 day time span, it would spiral away, and
1 day without 27 days.
you just it's 80.
88 days for its orbit. Yeah.
Yeah.
It's moving so fast, too. I think it's hauling. Yeah.
Just for exploration purposes, considering a three-body problem,
Yes.
which starts getting complex already, have you guys considered doing any numerical methods of approximation using nonlinear dynamics to see how things work?
No, because we're trying to do it in Tableau, and I don't know the R packages well enough to do nonlinear, but that would be interesting. I think with that, if we were to take and one of the things that I had wanted to get to that we didn't get to here was calculate the things that have the most impact on a body. And then say, okay, well, that's the biggest error issues. Let's focus on those. So then using a better method. But we didn't get there for this talk. Maybe next year. Yeah. Okay, there was another question. Yes. Here, I can't hear you. Let me come closer. Yes.
In the data source from NASA, you get snapshots recorded by NASA every 4 days, right?
From NASA, everything is on at midnight every day. So NASA's every day. For the calculations, we did every 4 days for the this right here. Yeah, yeah, yeah.
It's like 1 day, one.
And I would love to get even more data from NASA, more than just once a day. I think once an hour would be great, but I don't have that kind of hard drive space. Yeah.
You looked at, and just because I think about it, ESA Gaia satellite comms, that's a much cleaner data set.
I have. They focus more on the stars.
Yeah, it's more actually solar.
Yeah.
That is a clean data set.
I actually downloaded that data set, but I haven't gotten anything done with it. So, but I want to. I think the stars would be, and the exoplanets would be also be wonderful. Yeah. No, I think at Tableau we're just going to need to create some new science positions, and then I can have my wonderful dream job at my wonderful dream company. Yeah. So. Thank you. How are you guys having fun? Yeah. This is one of the last sessions of the week, so we were like, well, it's going to be nice and quiet. We're not going to have a full house, and All right, we've
As
got a lot
I
of
said-
bodies here.
I said before that this was sampling every 4 days. It was sampling once a day.
Oh, it's once a day, okay.
Yeah.
We-
Previously, we could get jagged acceleration or jagged velocity and jagged position. Well, the position was not quite jagged, but it wasn't as interesting because the errors did pretty much follow the same lines. So sorry to misrepresent that.
For the data sets and the flows that I'm publishing up, what are you guys super interested in? Is it the general cleaning or the actual data itself? A little both? Okay. So, and for the general data itself, I actually, of those info pages, I have all of the info pages, all the asteroids, everything, and I'll upload it as a,
I'm very interested in like your like section like the thing. I use Gravitation since I personally only got a lot of workflows prior to coming out.
yeah.
I'm still exploring how to look at those properly at that size. It's that interface between where they live and where it wants to be.
Yeah. Yes.
And so I know I'm not learning that efficiently, so I'd like to see.
What, it is hard for me to say that what I'm doing is the best because we have the devs on the prep team, they're just awesome. And they are burning through a feature list. They're like, oh, let's do this, let's do that, let's do that. So some of the things that I come up with when I first using prep, I created a pivot node, and this was before release, and it was massive. I had 63 nodes going this way, and then I joined it and joined, and it looked like a Star Destroyer. It was beautiful. And then they came out with a pivot node and said, oh, here, just use this instead. And so it was like, but it's awesome because as we're going along, I expect all these things these tricks that I'm doing, they're not going to be tricks anymore because we'll just have a node that'll do it. You know.
Are there things that you've done on the working side or you might consider moving to the website?
It depends on my audience, right? So if so if I'm showing this off and I want to move stuff around, I'm going to leave it where it's at. But if I wanted to do some good science, I would probably move it over and then bring it in. Yeah. In fact, the acceleration calculation, I moved to the prep side for this talk. Yeah, well, it was just
And for
easier.
the circular references.
Yeah, no circular references, and it was just easy.
So how did that solve the circular?
The circular reference issue is technically not a circular reference issue, but we put guards up to say,
Yep.
if you have these conditions, it's a circular reference. And we're going to file a feature request and see what kind of priority we can get on it. And I would love for us to be able to, because it would also solve the predator-prey model in Tableau. Well, almost solve that, because that does actually loop back around. But these guys don't, so, yeah. Yeah. No, that's okay. Oh, okay, yeah. So eventually, when we get supercomputers the size of Raspberry Pis, and I can have a stack of those, then I would like to do predator-prey models on planets in the solar system. And the other thing that we didn't get to on this one, is all the velocity we used is the sun. NASA treats the sun as stationary. And as you guys know, the sun's not stationary. It's whipping around the universe. And I'm very curious to see if that velocity will change any of these the error propagations. I think that would be interesting. Although I also think that would, yeah, but I also think that the 16-bit precision that I'm given is probably not enough for me to find that. So, but I'm still curious. I want to find out.
Well,
Yeah.
thank you all for coming.
Absolutely. Do we have to kick them out, or do we want to?
You're welcome to stay. We can talk as long as you're willing to.
absolutely. I don't know if there's a talk
but-
afterwards.